Software crashes when rigid code meets unpredictable real-world data volumes. A static array is the most basic way to store multiple items in a program, but it requires the developer to strictly define its memory boundaries at compile time. You have to tell the computer exactly how many slots you need before the code even runs. As this diagram shows, a static array is locked in a perfectly continuous line. This layout serves a physical purpose. It allows the computer to perform an instant O1 mathematical lookup of any index without having to scan the preceding items. We face a paradox. Fast algorithms demand this rigid, predictable memory layout, but user inputs arrive continuously at runtime in unknown quantities. If you try to push dynamic data into a static container, you overflow the boundary and trigger a fatal memory fault. Beginners often assume that variable-length arrays magically stretch to accommodate arriving data. They do not. The actual architectural solution to this problem in C++ is the standard template library's vector. Standard template vectors act as orchestration layers, managing memory growth through specific hardware-level maneuvers. To understand how vectors safely expand, we have to look at the two distinct battlegrounds of C++ memory architecture, the stack and the heap. The stack is blazing fast and highly organized, but it is strictly bound by small, rigid size limits decided when the program compiles. Look at the bottom half of this diagram, the heap. It is vast, dynamic, and capable of massive scale, but claiming space here requires manual allocation at runtime. Instantiating a new integer vector triggers an operation across both memory regions. First, a lightweight control object embeds safely into the rigid stack. This acts as an anchor, pointing a reference line down into the heap, claiming a dynamically reserved, contiguous block. This dual-nature architecture provides the absolute safety and access speed of the stack while weaponizing the vast scalability of the heap. To manage that heap space efficiently, a vector distinguishes between the data you actively have and the empty space it has internally reserved for you. This diagram illustrates size in the context of a vector. Size is the literal number of active elements currently populated by the programmer. Here, the size is 2. Capacity, however, is the absolute physical boundary of the underlying heap array before it hits neighboring unrelated memory addresses. A critical trigger condition occurs when you insert a new data point using the pushback command, and your size exactly equals your capacity. The computer cannot simply expand the existing array outward. Adjacent memory blocks might already be occupied. Instead, the vector executes a failsafe, requesting a completely brand new contiguous array elsewhere in the open heap. The new capacity follows a geometric growth rule, mathematically doubling the previous size. The copy phase begins, transferring old elements sequentially to the new array. Finally, the destruction phase wipes the old array clean, freeing original memory. Copying memory block by block carries a massive performance penalty. Because of this transfer, this specific data insertion slows down, hitting an O of n time complexity spike. We rely on the principle of amortized constant time.
While one insertion might be slow, the doubling strategy ensures that for every expensive copy, you earn thousands of nearly instant insertions. When averaged across millions of operations, the cost per element mathematically converges to O of 1. By intentionally over-allocating spatial capacity in the heap, vectors smooth out those catastrophic processing spikes into a mathematically guaranteed average. Knowing how this memory operates internally directly dictates the C++ syntax we use externally. We command the forward momentum of data ingestion using pushback, and we execute targeted data deletion from the end using popback. When we need to read through contiguous memory elements, the modern standard is the for-each loop. This high-level loop safely abstracts away the manual risk of requesting out-of-bounds array indices and triggering segmentation faults. But a hidden memory bottleneck occurs if you pass a heavy vector into a separate function by default. This defaults to pass by value. Pass by value forces the system to quietly execute a massive O(n) duplication of the entire heap array so that isolated function has a copy. To bypass this, we use pass by reference. Adding an ampersand operator grants the function direct access to the original vector, completely avoiding the copy penalty. Elegant syntax is only powerful if you truly understand the exact memory physics it triggers beneath the surface. Let's test this architecture on a practical proving ground. LeetCode Problem 136, single number. The constraints are strict. You must identify one unique integer hiding within an array of duplicates, using only O(n) linear time and O(1) extra space. Standard brute force solutions, like creating a separate hash map to count occurrences, instantly fail the O(1) memory constraint. To solve this, we rely on the lowest-level mathematical manipulation tool available to a programmer, the bitwise XOR operator. Algorithms translate human integers down to their raw binary representations to manipulate them directly at the hardware level. This animation illustrates the core cancellation rule of XOR. Any binary sequence compared against an identical sequence self-annihilates, resulting in 0. The preservation rule dictates the opposite. Any binary sequence compared against 0 remains completely unchanged. We initialize an integer at 0 and iterate. As each number passes the XOR filter, duplicates cancel out. Every pair annihilates, leaving only the unique value. Because XOR is commutative, order doesn't matter. Numbers find duplicates regardless of index. Algorithmic perfection occurs when high-level data structures are perfectly aligned with low-level hardware physics. Mapping out memory architecture reveals the vector as a precise calculated instrument rather than a mysterious black box. Begin your practical training on platforms like LeetCode. Focus initially on simple vector mutations that don't require nested loops. Your actionable challenge is this: write a custom function to reverse a vector strictly in place. Use pass-by-reference pointers in your function to mutate the data without triggering accidental capacity doubling or heap copies. Software engineering reaches its peak when the programmer moves past memorizing syntax to directly orchestrate the physical limits of computer memory.